We're very excited to have our last seminar speaker of the semester, Srikant. He's a professor at UIUC, works in a variety of different areas, but today he's going to be talking about policy optimization and reinforcement learning, and I'm really excited to see what he's got. So thank you very much for coming.
Thank you for the invitation. Delighted to be here. So I'm going to be talking about reinforcement learning with back. Probably all heard about it. This is joint work with my postdoc Yihan, my PhD student and at Winnicki, and two collaborators at NVIDIA. Dalal and Shie Mannor was also a professor in technical. So as all of you know, reinforcement learning has been in the news for a while. I guess it started with Atari game playing in 2013, then playing chess and Go and so on, and then it's now being used in robotics. So it's been successful in many fields. And the assumption in reinforcement learning is that there is an agent which takes an action. The action changes the environment that you're in. For example, you move a chess piece, changes the state of the board, and then you observe the new state and the reward associated with taking that action in that particular state. For example, in chess, there is no immediate reward, but there's a reward at the end. For example, either win the game or lose the game. Or if you're playing some kind of a video game, then each time you shoot something, you might get a number of points. So that's a reward that you get at each state of the action. But there are also many problems where there is no reward. There's no concept of a reward associated with the state or action. So in such cases, and I'll give you an example later, a human observing the experiment may be able to provide some kind of feedback from which you reconstruct something called the reward associated reward with each state of action. So this is basically the fundamental idea behind reinforcement learning with human feedback, because given a Markov decision process, so you have a Markov chain. Basically, most of the reinforcement learning assumes that what you're controlling is a Markov chain, and it's a controlled Markov chain. At each state, you can take an action. Based on that action, the probability you transition to a new state changes, and then you get a reward at each state for a given action. And your goal is to maximize the average reward or the discounted reward or something like that. But fundamental to all of this is the assumption that there is a reward associated with each state and action. So the problem that people studying reinforcement learning with human feedback is they study problems where there is no natural reward associated with each state and action. You have to infer this from some feedback that you get from humans. Okay, this is at a high level what this problem is about, and I'm going to give you a few examples. Blocking anybody here, but so I have talked to a couple of car companies that design electric cars with autonomous driving features, and also ChatGPT is perhaps the most prominent example in this space. But let me tell you what I heard from the car companies. So one example of reinforcement learning with human feedback arises in car companies where they basically have an agent, have a human sit in a car which has some autonomous driving features. And then they ask the human once in a while, do you like the ride? So for example, you may not ask the question for a human if the traffic conditions are not changing, you're going on a highway for 20 minutes, nothing has changed. At the end of that time, you ask the question, did you like the ride or not? So they give a thumbs up or thumbs down. And then maybe you decide to either change lanes or take an exit or move to a different highway. And you ask the question, did you like this particular maneuver? Then they again give a thumbs up, thumbs down. Again, maybe nothing changes for like 15 minutes, and then you ask the question, and then some traffic condition changes and so on. So it's like you're taking them on a long ride, and then every now and then you ask them, did you like the last portion of the ride? Which is different than asking it every time instead, because that's too expensive, and the human can't provide feedback every second, like this or not like this or whatever. So that's one kind of feedback that you get. Did I miss the slide? Yeah, okay, so I wanted to give this example too. Another example, another car company that I talked to, what they said is that they don't ask for explicit feedback from the humans. So what they do is they actually, before designing, so the other example that I gave you, you have an autonomous driving agent already, you designed some algorithm based on simulations in a lab or something like that. Then you ask a human to sit in the car and then ask for feedback. Another type of feedback you get is actually instrumented feedback. You don't actually explicitly ask people, whether they like the ride or not. You're actually having them drive a car before you're even designing your autonomous driving feature. So you have human drive a car, and then you have sensors that tell you how close you came to the car. Then you incur a penalty if you get too close. And then you ask how quickly they got to the destination. You get a reward for reaching the destination quickly. And then you get a negative penalty for violating traffic rules and so on. So these all can be completely inferred from instrumentation in the car. Sensors can completely infer this. And then you have, like, let's say 100 drivers drive your car. And then based on the sensor measurements associated with each driver, a total reward that they accumulated during their drive. And then amongst the 100 people, you pick the top 10 drivers, the best drivers, and then you do what's called imitation learning. You design your control algorithm to mimic the best 10 users on the road. So this is a different type of human feedback. A human is used to get feedback about who the best drivers are. Whereas this one, you actually ask them every now and then. So you might do this. In fact, a company might do both, because this might be done before you design your algorithm. And then once you design the algorithm, often this kind of human feedback is used to refine the algorithm. Okay. Because to do this, you already need an autonomous driving agent. Here, you don't need an autonomous driving agent. You do this before you design your algorithm.
Question?
Yeah.
Looks like in the second case, the reward is known, right?
Second case or the first case?
The second case, so your instrumentation based.
Yeah, they're the rewards. Exactly. They're the rewards known. You're only using humans. So you're only using humans to you don't know. You don't know what reward a human driver will get. So you have lots of drivers drive it and then get there, choose the top 10 or 10% or whatever, and then you try to do imitation. So this is a case where reward is known. But I just wanted to mention this also because there's a lot of things that come in the title reinforcement learning with human feedback. Here, the rewards are learned from instrumentation, and then you do imitation learning, and then you would further use this to. The question is are these the correct rewards? So that the interesting question is that we don't know if those are the correct rewards. So what people measure is getting to the destination quickly, and then everybody thinks the derivative of acceleration jerk is what people feel. So they measure jerk, and if the jerk is too high, then you think the passenger is not comfortable, but you don't know this for a fact. So what you do is the next stage, you would do this to further. Now you assume that you don't know the rewards, and you get the reward from this, but from the drivers. What ChatGPT does is something else, which is it basically generates an output. So it asks. ChatGPT is designed to act like a human. So if you ask it to write an essay on Abraham Lincoln, each time you ask it, it will give you a different output. So if there are 10 outputs, then you ask a human to rank these 10 outputs. And then from this, you infer some kind of a reward into the model. What I'm going to talk about is not really about ChatGPT, and it's not. I'm not claiming that it models ChatGPT in any way. But all it is you think of it as though that in the context of a autonomous driving feature, that basically, and let's say you take a human, you show them two different algorithms, drive them in a car, and ask them, which one did you like better? Okay, so what ChatGPT does is something similar to this. Okay, so this is the third type of feedback where you're giving outputs to humans and ask them the question, which one of these outputs do you like? And from this, you try to learn. So this is the model I'm going to talk about, but I just wanted to mention the other two models to let you know that this is not the only thing that people do. There are many other things people do. So I'm not claiming that. Talking about reinforcement learning with human feedback in general, but dealing with one particular model for reinforcement learning.
So ChatGPT already has, it's fine tuning the existing neural network.
Right. So you can sort of think of it as maybe first they've used some other type of human feedback or something else to design the algorithm. And then the next stage, some people use this in the context of autonomous driving, some people use this in the context of autonomous driving or ChatGPT. We're going to look at this model and make this more mathematically precise one. Okay. Yeah, usually it's done for fine tuning. So, so what is I've already said what reinforcement learning with human feedback is. Basically, the goals are hard to specify, or in other words, you don't know what rewards are. So an example that people give is a robot scrambling an egg, right? What is the reward at each time it's switched? Okay, so at the end of it, it doesn't break the egg, but it's the omelet becomes scrambled egg, tastes good, So when there is no number you can associate with each action that a reward. Okay. So this is something that needs to be learned from human feedback. And this paper by Cristiano et al. In 2017, we sort of started this whole area. They actually considered problems where many of the problems that they considered actually have actual rewards. And they said they played Atari games, for example, and you know the actual rewards, but they asked the human to observe and then also asked them to rate how the algorithm is doing. And then what they showed was that with less than 1% of, okay, so there are many states and actions that you go through when you're designing a reinforcement learning algorithm. By just showing the humans less than 1% of the data, they were able to dramatically improve the performance of their algorithm. So this is sort of what was the motivation for later ChatGPT using this. But they did this for Atari games, robotics. They gave lots and lots of examples, and they showed some of the trajectories to humans, asked them to label them, asked them to compare. They did many different types of human feedback. And they showed that typically they don't need that much data compared to the overall data that you use for reinforcement learning. Only a small portion is needed to get feedback from humans. But our goal is to try to understand why this is the case. Okay. So these are some pictures from Cristiano et al.'s paper. For example, it's hard to say what it is, but so the reinforcement learning algorithms are here, and the human feedback. I mean, where this is I believe it's a game where there is we know some rewards for this game, but if you use a human to get feedback, there's more variance, but the algorithm is quite close to what our algorithm achieves. So, as I said, we want to understand why RLHF only needs a small amount of data to be given to a human to get good performance, and we're hoping to get a theoretical explanation from the perspective of a particular type of reinforcement learning algorithm called policy optimization. Okay, so many things. Again, there's many things called reinforcement learning, many things called reinforcement learning with human feedback. So I'm considering one particular reinforcement learning algorithm and one particular type of human feedback, because this is many people have modeled ChatGPT, for example, using students with the policy optimization that I'll talk about, and this type of human feedback I'm going to explain more clearly. I'm assuming most of you have some Markov decision processes. So, but I'll just give a quick overview. So in a Markov decision process, there's a state and an action, and there's a reward associated with each state and action, which is what I'm going to assume. Okay. So in state S, if you take action A, you transition to state S prime with probability P, S prime given S. And then instead of maximizing the average reward, I'm going to maximize discount reward. Things that happen now are more important than things that happen in the future. And there is some fixed initial state, and then there's a policy. I is usually what I used it in my policy, which is the probability with which you take certain action, given that you're in the state. So the goal is to maximize the expected discounted reward. Yeah, so that's what we want to maximize. And then associated with that, there's something called the Q function. The Q function is basically says that if you take the current action A in the current state S, and then you use a policy pi from now onwards. Current state alone, I'm going to use an action A, but after that, I'm going to use a policy pi. The total expected reward that I get, or the discounted reward that I get, is what I call Q pi. And this is a quantity that would be useful for us, because if you know Q pi, then the optimal policy can be read off by maximizing over a Q pi estimate. When I did stochastic control MDPs in the late 1980s, there was slow reinforcement learning, but one of the algorithms we were taught is policy iteration. I sort of wanted to start off with policy iteration because it explained reinforcement learning quite easily once you know what policy iteration is. So policy iteration is that you assume that the Q function is known. Okay, you start off assuming some Q function is given to you. And then you find the best policy by taking the R on that. So this would be a deterministic policy because we're just maximizing over A. So there is not the phi A given S is a little bit redundant here. So I can just call it A star, but I just want to call it phi A given S. And then you compute the value function associated with that policy. So this can be obtained by solving a fixed point equation. And then you go back and pretend that this is the correct Q function, and then obtain a new policy, and then you keep doing this over. So this is called our algorithm of policy iteration, which is one of the staples of Markov decision processes. Okay. Most policy optimization algorithms in reinforcement learning are basically approximate versions of this. Okay, how to implement policy iteration approximately. So here's one way to implement it approximately. So one issue here is that the policies tend to be deterministic. You take a particular action in a particular state, which means that you may not visit some state action there. So first of all, you want to use randomized policies, but you also want to use policies that are close to what policy iteration does. So the most natural way to do it would be to say that the new probability of choosing action A times S is the whole probability multiplied by E raised to the power of eta times Q. So if I let eta go to infinity, this would pick the action with the which maximizes the Q function. Clear? So it just simply takes this previous policy and randomizes it. Okay. So it's a randomized approximation to the previous policy. Okay.
Sorry, should there be a pi A given S on the right hand side?
This is what people do for various reasons. Yes. So you take it and make it proportional to the previous thing multiplied by this. You could also do one without that.
So pi A given S was 0, 1 basically, right?
No, so in this case, I would start off with a randomized policy and then keep improving it like this. But if I said eta go to 0, then it will still give me the, sorry, eta go to infinity, it will still give me the max Q pi A. Right.
I'm just confused because it seems like you have a pi of A given S on both sides.
Correct.
And it should
Yeah.
So this is like
No, sorry.
a previous iterate and a next iterate.
This is a computer science notation. This should be pi k plus 1 equals pi k.
Yeah.
Okay. Yeah. It's like you write equals to programming languages, it automatically says what something like that. That's not that. Yeah. Yeah. Sorry. That should be pi k plus 1 equals pi k is proportional to pi k times that. But it's often written like this for convenience, but it's a good question. Clarifies it. And then what you do is then you get samples from your policy and estimate. So you don't know how to figure out the value function for this policy, and then you collect samples from a trajectory generated by a new policy and estimate the value function. So both of these blocks are done approximately compared to what was the previous page. The previous page, you find the best optimal policy for the current Q, and then find the new Q exactly, and so on. And reinforcement learning, essentially, this is approximation. Okay. So some of you may have heard of something called PPO and TRPO, which are like wide, super famous practical algorithms that are used in reinforcement learning with great success. And those are all essentially variants of this. Okay. So instead of doing this, they do something slightly different. But this part is also it is similar to what is done in TRPO. TRPO is probably the most widely used algorithm in robotics, and it essentially comes from this. Although then, if you look at the papers, you won't see that this is what it is, but this is what it is. So the other thing is that, of course, the state and the number of states and actions could be very, very large. So you cannot expect to learn the Q function exactly. So you do some sort of functional approximation. You assume that associated with each state of action is a feature vector that right now I'm going to assume it is known. Normally, you would use a neural network to extract this, and depending on the time, I'll talk about how to use neural networks instead of a known feature vector here. But let's assume that there is a known feature vector multiplied by some unknown data that represents Q of SA. So typically, if S and A could be, S could be in the millions or billions, and A could be typically smaller than most of the problems that I consider, but S could be very, very large. Whereas theta would be the dimension of the size of the number of parameters in the neural network, which could be, depending on the problem, again, theta could be in the millions, and this could be the order of trillions, but there's a huge dimensionality reduction going from theta to the size of the state space. And you want to learn theta from the data in policy evaluation. So the previous policy update that I had here, if Q is approximated as phi transpose theta, can then be written in this form like this. So, and now I have proper. Here's the same thing, the new policy is the old policy, multiplied by A is the power thing divided by the summation to normalize. Is clear? Okay. So to evaluate the policy, so what I did in the previous page was, so I took the first block and expanded it further by saying that Q is in this form. So it has to be like this. Now I'm going to look at the second block and tell you how samples are collected from a given policy. Okay. There are many ways to do this. The most efficient way to do this is what's called TD learning. But I'm not going to do TD learning here. I'm going to do what's called Monte Carlo sampling. But basically, Monte Carlo sampling is forget the what's the slide. Essentially, you start at some initial state, and then you add up all the rewards that you get weighted by the gamma, so that gives you an estimate of the value function. Do this from different initial states, and then try to fit the best straight line from straight line. So it's a data transpose. Okay. That's easier to analyze in this context. So we are doing this. TD learning will definitely be more efficient. Okay. I try to explain a little bit more as to what. So what you have to do when you do when you generate a trajectory is first you have to generate an initial state, and then you have to generate a trajectory starting from that. Both of them are done through some randomized process. You keep there is an interpretation of a Markov decision process where gamma is the discount factor. You can think of the Markov decision process stopping at each state with probability lambda, or continuing with probability 1 minus gamma. So I'm using that interpretation to approximate the expectations. Yeah, power H here. Sorry. Okay, so as I mentioned earlier, the robot scrambling an egg is the goals are hard to specify. So potentially one can. So I can implement this algorithm immediately. I mean, so this is what's widely done. As I said, PPO or TRPO or variations of this. If the rewards are generated, if the rewards are known, I can just compute, estimate the Q functions, update it, estimate the Q function again, and keep repeating this. So our problem starts because we cannot do this estimation because the rewards are there. Okay, so this is the you're going to be with. So because our S comma A cannot be directly observed, the lower block in the policy optimization process cannot be performed. Okay, so what do we do? Okay. This is the question. So what the reward learning does is, I'm going to first consider a simple version of the reward learning process. But basically what you do is you show two trajectories to people, and then ask them which trajectory you like better. Okay, and you keep doing this over and over. So you can think of this as showing two trajectories to 100 people, and in reality, what we about thousands of people. In reality, what you would do is you would select about 20, 30 people and show each of them many, many pairs of trajectories and ask them to compare. Okay. And the modeling assumption is that the reward is also parameterized by the same feature vector phi. So I said the Q function was phi transpose theta, but I'm going to assume the reward is also phi transpose mu. Okay, so the phi is a known function, and mu is unknown. So the total reward associated with the trajectory, here, like I said, again, forgot the gamma, but the total reward, if you ignore the gamma, set gamma equal 1 for this theory now, then the total reward associated with the trajectory would be this. So when I show you a trajectory, I know what the summation is. I am trying to learn mu from what you tell me. When I show you two trajectories, I want to learn the mu's. So I know this summation for the first trajectory, and I also know this summation for the second trajectory. So I'm somehow trying to learn mu from what you tell me. It's clear. This is basically the human feedback problem. And this is a classical model from psychology. It's called the Bradley-Terry model. According to the Bradley-Terry model, the probability that you would like trajectory 1 over trajectory 2 is proportional to e raised to the power of the reward associated. Okay, this is a widely used model, comes from psychology. Whether this is accurate, this is an accurate model or not, nobody knows, but it seems to work very well in practice. So this is the interesting thing about it. Right, so this is called the Bradley-Terry model, and is applicable way beyond reinforcement learning with human feedback. Always whenever there are comparisons made and people are shown two objects and they compare one versus the other, you assume that they do it because the reward associated with it's proportional to the e raised. The probability you pick one is proportional to e raised to the power of course. I mean, R's are very, very large. I mean, even small numbers, e power 10 is so large in this one. So if you have to normalize and stuff like that, so ignoring the betas and stuff like this constant there, or you can normalize the rewards to 1, you can do it.
Question again?
Yeah.
So you ask the person to evaluate for an entire trajectory, not at every stage of the state action.
So I give them two trajectories and I ask them which one do you like better. That's it.
But you could also ask for each state and action whether you what was the reward.
Because people can't. The idea is that, let's say you're thinking of self-driving car. I mean, there is no reward associated with each. I mean, you just ask if you like the ride, for example.
You could break it up too in different.
Yeah. So that's the other example. Here I'm assuming that. So we are actually working on it. So far, actually, we have extended it to that case that you asked. You can also break it up and ask the same question. So far, we're not able to prove that it's better than this. I think it should be better. Theoretically, we're not able to show you it's better. We're getting the same results, so I'm not explaining it. Yeah. So we're trying to work out how to. What is the impact of slicing and how much does slicing improve the performance of our algorithm? We don't know yet. Yeah.
Are the trajectories like is H like where you truncate the trajectory or do
Yeah, you just run the trajectory for a certain amount of time H.
Okay.
And you just stop it and show.
so there's no like terminating thing, but H is like a imposed thing.
Yeah. It's just. You could also terminate it, I suppose. I don't think it'll. I mean, you could also let the mark out decision process be classifying the probability gamma and then stop it. I think it will have slightly modify this and it will also work in that case. Yeah. It doesn't have to be fixed H. Yeah. I do allow that here. Actually, H could be a function of the trajectory. So trajectories could have different. Yeah. So then it becomes a maximum likelihood estimation problem. So I just give you lots of pairs of comparisons, and then I need to estimate this parameter. To estimate this parameter mu, I can do this from maximum likelihood. In particular, if I show you lots and lots of trajectories of the same, if we show you the same two trajectories multiple times, then essentially the fraction of time you prefer one or the other is exactly equal to this probability in the Bradley-Terry model. And so essentially you can invert it. A more precise way to say this is to use maximum likelihood estimation. So you don't go look at the formulas or anything like that, just basically maximum likelihood estimation. What is the mu that maximizes the likelihood? And this was already studied for our work by Michael Jordan's group, who showed that the error in estimating mu has some. Just look at this plot, this one over MHF. So basically, if you show MHF pairs of trajectories to people, then the estimate of mu becomes more and more accurate at rate 1 over square root of m. Okay, that was that result. It's clear what the result is. So if I show you multiple pairs of trajectories, or you can think of it as I'm using MHF humans and showing each one of them a pair of trajectory and a pair of trajectories, and as I have access to more and more humans, then the rate at which I'm getting accurate is going down. Okay. So we want to use this result in our problem. So basically what I'm going to do is now completely decoupling reinforcement to the human feedback part from the reinforcement learning part. I show people lots and lots of trajectories. Let's not worry about how these trajectories are generated at this point. Let's assume that there's some kind of independence amongst them. So they're rich enough to get the data that you want. And then I'm just going to do reinforcement learning, assuming that I've estimated the rewards from this part. So it's completely decoupled. Okay. Decoupled in the sense that, of course, any error here will propagate and give you errors here. So that's what I want to characterize first. I mean, that the process is decoupled, but an error here will lead to an error here. I want to understand what the error is. Okay. Yeah.
So you're basically learning some approximate function of the reward.
Sure. I'm estimating an approximate reward function.
They're just deterministic rewards. There's no.
Yes.
So when I play my reinforcement learning, I just
Use those rewards.
use that function.
That's it. But I want to understand how much this is going to affect this. And this is the crucial part of the result. Okay. So the main result is which mostly captures most of the talk. The rest of the talk is adding bells and whistles on top of this. Says that the amount of human feedback, the error due to the human feedback portion here, which according to Michael Jordan et al.'s paper, gives you a 1 over square root of m accuracy in the reward, gets worse when you pass it through the reinforcement learning algorithm. It becomes 1 over m power 1/4. Okay, the rate at which you're getting the correct answer for reinforcement learning. This is the difference. If you run a reinforcement learning algorithm, this is the optimal, the value function associated with the optimal policy. This is the value function associated with our policy with the reinforcement algorithm spits out. And there are multiple errors associated with it. There's an error that cannot be, nobody can do anything with this thing. It's a function approximation error. If my ability to approximate the Q function is not good, there's nothing to do. But if I run my reinforcement, those two boxes that I showed, if I do those loops t times, then the error goes down to 1 over square root of t. And the error due to, in the second box, there's 2 boxes in the reinforcement learning algorithm, one which improves the policy and the second one evaluates the policy. If there are m samples that I use every time in the second box to estimate the Q function, then the error due to that is m raised to the power of 1/4. And if I do m human trajectory comparisons, then the error due to that is m power 1/4. Okay. So the way to think about it is that here, so yeah.
So you had some bias there due to your value function between. Wouldn't you have some bias there due to your reward function approximation? Like even if you have infinite humans, you wouldn't be able to learn the true function.
Yes, that's correct. Here we are assuming that part is, I mean, we have to add that 2 to that, but I'm just assuming that is accurate. That's the P transpose data, that's just there. Yeah, otherwise we'll get an extra term there too. Yeah.
So just clarifying question, the bias that you have, is it the approximation error in whatever the true function is, and its approximation by the basis times mu, basis function.
Sorry,
times mu.
this function approximation error is due to the value function. I am not showing the function approximation error. There are 2 things that I'm estimating. One is the value function Q, the other thing is the reward R. I'm only showing the bias due to the value function approximation. I'm going to assume that the reward is truly, I guess that was Martin's question too, the reward, I'm going to assume that this is exactly like this. That there is no bias here. I mean, if I cannot approximate this, I cannot approximate this. So, but strictly speaking, I should have also had a term here that includes the extra bias for the reward. So this is interesting because if you look at the total number of samples that I have, that I'm using, each time I run my reinforcement learning algorithm, I have to run stochastic gradient descent to learn the Q function. So the total number of samples that I use in reinforcement learning is T times MSDB. And top of that, I have human feedback. So the total number of samples that I have is T plus MSDD plus TMF. Because the order of these two are the same, the ratio of this goes to 1. So what do I implement? Let me explain it carefully. So suppose I want to have an error of 3 epsilon here. And I can 1 epsilon do for this, 1 epsilon for this, 1 epsilon for this. So MSDD will be 1 over epsilon power 4. And this is also 1 over epsilon power 4. So what I'm saying is that the total amount of error that the total number of samples I need, the total number of samples I use is T times MSDD plus MHF. Since these two are in the same order, the ratio of the amount of human feedback to what I would do when I have no human feedback, when you know the rewards exactly, goes down as 1 over T. So this is the main result. And by saying that this is kind of obvious, it's not obvious for the following reason. It really depended on how much worse. So if there was no reinforcement learning, just to learn the reward, the error goes down as 1 over square root of m. But now it has become 1 over m power 1/4. If it had been 1 over m power 1/8, then this wouldn't work. Right? These two will not cancel off. And this will not work. So what I'm trying to show is that the error propagation from learning the reward to its impact on reinforcement learning is just the right amount so that this ratio is actually going to 0 if you're on the reinforcement learning algorithm for video. So I said the same thing again on the slide. The key insight from analysis, the fact that the number of samples that you need to estimate the value function is approximately in the same order as the number of samples needed to estimate the rewards, actually is very important. I mean, of course, if this was better, it's even better, but at least it's no worse than this. And so therefore, you can prove that the amount of human feedback that you need compared to the total number of samples that you need to reinforce. Okay, is the main result clear? Yeah.
Wait, so when you said you were splitting epsilon, that also means that 1 over square root of t is also epsilon.
1 over square root of t will be equal to epsilon, which means that will be rho as 1 over epsilon squared. Correct.
So wouldn't you still have small human feedback if it's
No. What I'm saying is that
instead of having 1 over t, you have 1 over square root of t or something?
so this is the ratio I'm interested in. T.
Yeah.
Yeah. So this, yeah, you're right. I mean, if actually what we will see in the simulations is that this seems to be almost exact in the simulations.
Yeah.
Okay, so what is your question?
So my question is that the NHF is 1 to the power 1/4 and the other 1 to the power 1/2. Like NHF, it's like t squared. In this case.
MHF is like epsilon power 4. I mean, so
Yeah.
it's epsilon power. This is epsilon power 4. 1 over epsilon power 4. This is 1 over epsilon power 4, and this is 1 over epsilon squared.
So you still have some
Slack.
wiggle room.
Yeah.
For
So let's see how much wiggle room there is. So for what I was trying to say here is that I don't think that will work.
maybe 1/8 is the
Yeah.
threshold.
Yeah. But what is interesting is that in the simulations, you'll see that these two seem to be actually on the same order. Because this 1 over t is almost exactly the simulations. It's kind of interesting. But yeah, so I think Martin's point is valid. These are all upper bounds, so I don't know if these are tight. So there might be some ways to tighten it and maybe you can get at the downside. But at least the initial simulations that we have done seem to indicate that this is correct order. But I'm not 100% sure of this. Yeah. So it at least shows that this ratio is going to zero. Whether it goes to zero at an even better rate than what I have shown here, you're right. That's very possible. Yeah. That's a good question. I think I have that in the open problems at the end. Okay, so the rest of the talk is bells and whistles on top of it, mostly for theoretical reasons. Basically, I've written everything in full notation here. There are hidden constants here, which I don't have a very good handle on, and there are ways to make the hidden constant to give you a better insight on the hidden constant. So one problem here is that I have to make some assumptions, which I did not state very clearly, on how I get my result. Ignoring the equations here, essentially the idea is that I have to have a rich enough set of trajectories to estimate both the Q function and the reward function. Whether I have a rich enough set of trajectories is something that's not clear. So there's a nice paper by Agarwal et al. From 2020, where they give an idea of how to make the set of trajectories that you're using to, they don't deal with human feedback. We're basically adapting the idea to human feedback. The idea is that instead of using the current policy, so we are going to, so from now onwards, I'm going to assume that there are two policies that we're using. One is called a baseline policy, and the other one is a policy that my reinforcement learning algorithm is choosing. The baseline policy is always fixed. The reinforcement learning policy is what I'm, with the policy that I get from reinforcement learning is what I'm comparing always to the baseline policy. Now, the new policy that you get every time may not be rich enough, because as you are getting the reinforcement learning algorithms working very well, you're going to get deterministic policies in the limit, which means you're not going to visit most state action pairs, in which case the comparison is not going to give you a lot of good answers. So the basic idea of what Agarwal et al. Suggested is that instead of using this, suggested in a different context, but what we are going to use is that use the average of the last n policies rather than what is average with probability 1 over n pick one of the policies in the past, rather than using the current policy. That makes the structure, the exploration richer, and so you will have less problems with the assumptions that I did not show that are needed to make some point. So this whole OTILDA result and assumptions, this OTILDA result is also contingent on some assumptions, which I'm not putting up here. But essentially, the assumption says that reinforcement learning algorithm should be generating a rich set of trajectories, which I know definitively it's not true, because as time goes to infinity, you will not be generating rich enough trajectories. So to avoid this, we have this other algorithm, which fixes the issue. I'm not going to go through this details, and I get there are some additional, it gets worse in some ways, but it gets better in some ways. So it's not, I won't go into the details of this. Is something called counter loop iteration, which I did not get into. So it gets worse in some ways. But the essential message saying that the fraction of data that you need for human feedback still goes down as 1/3. That part is still correct. But these bounds get worse by a factor of square root of n here, which is some other parameter which I did not spend time on today. But the essential message still remains the same, and it removes the mathematical discomfort that I had when I wrote the previous theorem, which is basically making some assumption that I know is not a very good assumption. So now this helps eliminate that assumption. But you can essentially forget about this. The fundamental idea is the error due to human feedback, and the error due to estimating the reward function, and the error due to estimating the Q function are roughly the same order in terms of the number of samples. I think this continues to hold while I can remove the uncomfortable assumption that I had previously. You can extend all of this to instead of assuming that the Q function and the reward function are some P transpose theta. this is not. So basically, yeah, I don't want to spend too much time on this. Basically, you can assume that the neural network is learning this. Okay, so you don't have to use pre-specified value functions. I mean, pre-specified linear assumptions. And you use a neural network here. Our analysis only works for a single hidden layer neural network. This is called the ReLU function. So it's a single hidden layer neural network with ReLU neurons. And you can use the same algorithm, and you get the result here. But the result here is not, I don't know if this is how good this result is in terms of how accurately it captures. So let's focus on three terms. So these two terms are similar to what we had before. Ignore this term, it's not that relevant. But this is the new interesting term. This M is the number of neurons. What it says is that the error that you have scales as 1 over m power 1/16. Meaning if M is the number of neurons that you have, you need to have a massive number of neurons, which is true in practice. People do use millions and millions and billions of neurons, but I don't know, m power 1/16 seems probably a little too much. So I don't know if there's a way to, all this result says is that if you use a sufficiently large neural network and capture the previous result without assuming the linear function approximation. That's the correct way to think about it. I wouldn't give a lot of weight to this term. It's just simply, at this point, it's a mathematical artifact. I don't know whether you can do better than this or not, but it just simply says that as the number of neurons increases, you can throw away that linear function approximation and you can just learn features, everything from using it. Okay. And we did some experiments. This is a particular example that the Agrawal 2020 paper used, and so many people use it as a comparison. So we compared our results with the Agrawal paper's results. So the Agrawal paper essentially takes this MDP, which I don't want you to go through carefully. It takes this MDP and then just runs policy optimization on it. And these are the results that they got. Okay. So the result that they got, this is the suboptimal algorithm. So it's a true V minus the V that your reinforcement learning algorithm gets divided by V star. And using 50 iterations of reinforcement learning, you can see that if you use reinforcement learning with human feedback, the number of human queries that we need is 125,000 compared to 1.3 million trajectories that we have to generate otherwise. And the ratio of the query to sample complex, the ratio of the number of queries, the ratio of the number of queries to the number of samples that you need for reinforcement learning is like 1%. And if we double it, it becomes half. This is what I was saying, surprisingly accurate. And if we make it 4 times, it becomes almost exactly 1/4. I mean, we haven't tested this on things like ChatGPT or whatever. But this is for this particular example, it seems to almost exactly match the results that we have.
So for these experiments, you're assuming epsilon bias is 0?
No. We're not assuming epsilon bias is 0.
So what did you use for your?
I guess it's a rich enough neural network. So I guess the bias due to the neural network will not be significant here. Good question. Yeah. So there is no, I guess one of these questions is that these results should only fall outside of the epsilon bias. But if I guess the problem is neural networks perform much better than what we can show theoretically. So even though there's an epsilon bias in all the papers, neural networks somehow seem to have very little. This epsilon bias is so small if you use a sufficiently large neural network that it doesn't seem to affect the results. Yeah, that's something that no theory can really still capture properly.
If I were to raise that, if you look at your previous result on the neural network, you have n to the power 1/16. Is that you use neural networks for both, I guess, the value function and the reward? So why do you still have like a constant bias there? What did that?
So there is an additional thing that you have to do to show that. uh, This is not a, yeah, there is still a bias term because, that's a good point. There should also be a function of temp, so there are two things, so if you use a neural network of a certain size. As m becomes larger and larger, the bias should go to 0. And then, there is an additional factor due to, let me think. Okay.
Error being amplified from the reward is amplified, and that's.
Not only that, but you're running MSGD iterations of in both cases, you're running some kind of a algorithm to fit the neural network parameters, and you're not letting that run to infinity. So there is an error due to that. And we to let the if you sort of using gradient descent, let's say there's some magical algorithm that minimizes the difference between the two, that factor will not be there. So what I'm saying is you're only, so this is not, so the neural network is approximating the function, but the neural network is also not trained to infinity, right?
Yeah.
So there is an error due to that.
Yes. So then this M is about the reward. So the neural network that is approximating the reward, right? That M is that.
And the Q function. So we are using a neural network to approximate both the Q function and the reward, and then you're not training into infinity. Okay, training into infinity is also problematic because you have to do something called early stopping for the analysis to work. So there are lots of getting. We'll see.
So are you saying the epsilon bias part of it captures the ability of M neuron of the neural network with going to infinity? You're basically allowing it to train as much as you can. What is that? That's part of it?
That's true. So I think here we did not take into account the representation power of no, that's correct. So sorry, what was the question? Say that again.
So this is somehow capturing the ability of a M neuron, M layer
Correct.
neural network.
Correct.
If you can train for infinite amount of time.
Yes. Well, no.
It's somehow capturing both the expressiveness of the neural network with M neurons and the.
Right. So again, this question is, if M goes to infinity, is this going to 0? Yes. No, if M goes to infinity, this will go to 0 actually.
This will go to 0.
Yeah, but the problem is that what I'm saying is that there is no proper expression that says that if I use M neurons, okay, if I use M neurons,
I could fix M and let the training go to infinity.
the training go to infinity. Correct. So even then there will be a bias here,
Yes.
right?
Yes.
And there is a 1 over M power 116. I believe that this is because of the training the neural network. So because of training the neural, because you're not training it. I mean, because I'm only training it, so I think the assumption here is that every time I get a sample, I do one iteration of gradient descent. I guess in practice, you could keep going through the same set of data over and over again, but then that induces correlation and we don't know how that works. So we just assume that as we get the data, we just run it once and then stop it. But in practice, people keep running it through it. So, yeah. Okay, so the main insight is that the number of queries divided by the number of total number of samples goes down to 1 over D. So here are some interesting open problems. So as I mentioned, we don't know yet how to analyze the thumbs up, thumbs down model for segments of trajectories. Like we will be asked, instead of asking what the entire trajectory is supposed to segment the trajectory and then ask either the thumbs up, thumbs down, where you're not comparing, but you're just simply inside each one, or compare two trajectories, but ask them to compare portions of the trajectory. So we don't know how to do this, or at least we have some results, but they don't seem to improve on what we already have. So I think it's a problem with our analysis. That we're working on actively. So some things,
Even just as a modeling question there, it's not clear, how do you interpret thumbs up and thumbs down?
there is also a modeling, parameter model for that.
You have like something like the reward is above some threshold or
It's some softened version of that. A continuous version of that. So there are,
with like this exponential?
yeah. So there are models from psychologists for that too. So, and I don't know about whether the dependence on MHF is optimal. There is some wiggle room. I don't know if they do better with the MHF. There is still an assumption, which I did not get through. I assume that the baseline policy is rich enough. We are always comparing the policies that we get out of reinforcement learning with the baseline policy. I'm assuming the baseline policy is rich enough, and I didn't precisely write down what that assumption is. How to generate a baseline policy that satisfies the assumption is something that is interesting and pretty interesting to think about. And as I said, we use Monte Carlo policy evaluation because it made some parts of the analysis easy. We use TD learning, which is a more efficient way to do policy evaluation. We don't know how to do the analysis yet. But I think the main point is that this is we're able to demonstrate this. I can imagine that with TD learning we do better, and because the number of samples you need typically for TD learning in practice is much smaller than what you need for with Monte Carlo policy value. The paper by Dan Russo and student pointing this out in the last year or so. I think these are the references. With some references in the paper. Thank you. So the question that
I don't know what it's. When's probably related to this segmentation stuff that you're saying, but if you're showing like, for example, true trajectories to some human observer. That you said you ran it for some time H, that can be trajectory event. So how does it affect, like, the longer the trajectory, should we get better feedback? Or I don't know if that affects, so that's in the wall of it.
I think we are assuming that the trajectory is truncated using the gamma parameter. So we haven't really thought about what if you deliberately run it for a very, very long time. There has to be some rule to truncate the trajectory. There could be two sets of rules. One is use a fixed trajectory, or you can use the gamma parameter that's already in the MDP. We are using the latter one, but the result will be identical in the other case too. But the question you're asking is that what happens if the length of the trajectory is increased? How does that affect the result? You get better results or worse results?
Or decrease, since like splitting it, it's just you get to reinforce over smaller trajectories instead of.
Yes, but the problem that is this correlation, and we don't know how to analyze that. Okay, that I believe is true. If you split it into smaller trajectories, like you said, or we said, I mean, we definitely should have. We thought that, we tried to analyze it, we're not able to analyze it. I don't think there's a problem with the analysis. I'm not claiming that it's.
So the chunks get correlated, that's why.
Yeah, the time gets correlated, and so we don't know because it's from a Markov chain, so we don't know how to analyze it. It's difficult. Whereas the two trajectories are independent, starting from initial position. You know, it's independent. So this is we don't know how to analyze it. So it's purely a matter of not able to analyze it. Yeah, definitely there's a better strategy. Yeah. Any other question?
Yeah, I did have, like, this is very surprising to me that you get one or two. Do you have any intuitive explanation why you need so many less samples from human?
Yeah, it's not. Okay, I won't. So So there is the Michael Jordan result, which is nothing to do with reinforcement learning, just basically comparing trajectories and learning rewards. to convert that, what happens in reinforcement learning. I don't have a very good intuition of it, just simply is a mathematical exercise. Whether it's exactly the same question, because Paul Martin's asked the same question, whether I gave this talk at MIT and Martin Wainwright asked the same question. So I don't have a very good insight on how this, whether it should be M power 1/4 or whether it should be something else. It just happens to be M power 1/4, and so it nicely cancels the negative one over the result. But I don't know if this is tight or I have no idea, because it just basically you take that other errors, put it into the errors that you get reinforcement learning, you just post off and through the calculations, and she came up with 1 over M power 1/4. I've looked through it multiple times, and we've been trying to figure out if this is the best or not. So just purely calculation based result at this point. Yeah.
So the Michael Jordan result was what? Was just on the reward function explanation.
Michael Jordan result was just simply about comparing pairs of trajectories and then learning the reward from it. And then they showed that as the number of trajectories increases, or the number of humans to show it increases, it goes down slower. But when you plug it back into the reinforcement, it becomes 1 over M power 1/4. Whether that's optimal, I don't know. Any other questions?
Okay. Thank you, Steve.